Hello, so my name is Nicolas Delemarre, and I'm a field application engineer working for Lauterbach. So for those who don't know Lauterbach, we are selling development tools, and here especially debug and trace tools. So the challenges that embedded developers are facing today are obviously driven by the market requirements, and thus the embedded systems and chip architecture are becoming more and more complex. So as an example, of course, there are heterogeneous systems, so many different cores can be there, and so it results in different scenarios such as SMP or AMP debugging, but we will talk about that a bit later. You could also have different OSs, so typically a rich OS like Linux, for an example. So that's another example. Also, there is AUTOSAR OSs. Well, in conclusion, we in Lauterbach are seeing more and more complex systems with different OSs, hypervisors, and thus it requires efficient debug tools, and that's where we are focusing on. So about RISC-V debugging. So you have a simple example here. So you have a basic implementation where you have a RISC-V heart connected to a debug module. This debug module is basically providing the basic debug mechanisms, and this debug module is connected to a GMI, and then connected to the debug transport module, which is basically the interface to the outside world, so the so-called debug port. It's a really simple implementation, but it works pretty well for even more complex systems. It's quite easy to adapt, and we of course follow the ratified debug specification, so I'm speaking about version 1.0. So now we will focus on the trace. So for those who don't know, I like to give an analogy. Basically debugging is like taking a picture. So you stop the program, the CPU at a certain time. You can see the PC, the registers, the memory. But in fact, you're just controlling the core. You can eventually stop the peripherals if the logic is there for that, but you cannot stop the surroundings. And this is where the trace is being useful. So the trace, I'm speaking here about a real-time trace provided by the chip itself, supplements debugging. And from there, you can use several features, and of course, feel free to come to our booth later to see what it looks like. But this video can be replayed either onwards or backwards. On the other side, you can, of course, thanks to this video, you have all the timestamps that comes with it. So you can do any profiling measurements and see if your interrupts are correctly called every 10 milliseconds and so on. And also, as you are tracing the instruction flow and sometimes the data trace, you can, of course, do some code coverage measurement, and can go from object code coverage to MCDC code coverage for safety critical application. This is typically what is required. And all that is on target without any instrumentation. So as of today, well, there are quite plenty of trace possibilities, but we will only talk about the two standard versions, so the so-called ntrace and etrace. We at Lauterbach support both of them. They rely on different documents as shown in this picture. And the nice thing to underline is that they all rely on the same trace control interface specification and the same trace connector specification. So it's really easy to switch from one to the other, and also from our side, it's much more easier to support because we don't have to mix things up. Yeah, okay, so, well, here what I wanted to underline is that there are quite some capabilities that comes with the trace. It works pretty well even on multi-core systems. There are flexible ways to access the trace component, so it could be from system bus accesses or through the DMI, but we'll see that a bit later also. You can also use some filters to filter the trace, to trace only the things that you are interested in. For example, And of course, yeah, as mentioned, we do support both a ratified version of eTrace and nTrace in various systems that we already faced. Now we can quickly compare the two standards. Well, the idea is not to say which one is the best, because it will always depend on your project and what you want to achieve. Typically, as a starting point, you can see that one does only instruction trace, while the other do also data trace, which can always be useful to trace some registers, peripheral registers, or even some global variables, so some data structures. But in the end, they all have their drawbacks and their advantages. So it's always a matter of choosing in comparison with what you need. But here is a list of what they both did. Here is a simple implementation of a system like this. So you can see that there is the debug side with the DMI and the DTM, the debug transport module, the DTM. And in green, you can see that there is the trace components. And you see that there is a trace encoder. Here it's a Nexus encoder, so for nTrace, and one trace sink, which is basically a non-chip tracing. So it means that the trace will be saved in some memory in the chip. So this is really simple. You see that there is only two components accessed by the DMI and nothing less and nothing more. But you could also get something like this, which is a bit more complex. You see different art. Well, there is also several trace encoders. And in the end, you could also have some generic cores, but it could typically be an ARM core, because this is typically what some RISC-V cores are meant for. And there is an ATB, which is basically the core site ATB bus. So for the transportability, you could have one trace stream in the end with all the trace from all the cores. And we can trace all of them at the same time and debug them at the same time. They all rely on the same PIB interface. It could be either on-chip or off-chip, so the trace could be retrieved in one of our tools, for example, so not relying on some memory in the chip. So this has the advantages that you can trace for a longer time, and especially also that we can imagine some use cases where you would have some trace memory into a buffer in your chip, but for some reasons you could face some corruption in your memory, so the trace buffer could not be used at all. So if it's saved in our tools, it's the safest place the trace could ever be. Yeah, and last but not least, I wanted to underline that we are not followers at Lauterbach. We are really early adopters. We participated a lot into all the debug and trace specification, providing our thoughts about this and how to do some of the things that were needed. So yeah, we are definitely early adopters. They are working closely with a lot of people around this. As a summary, so chips are becoming more and more complex. Systems are becoming more and more complex due to the number of cores or the number of the OSs. We do support the RISC-V External Debug Specification, so version 1.0. We do support all the trace standards, so either in eTrace or nTrace. We have been strategic members. I just talked about this. And yeah, there is a link to our solutions here. But if I recommend you something, is to just come to our booth. I don't remember which number it is, but it's upstairs. You can't miss us, I believe. It's close to where you can have some food and so on. And yeah, thank you for listening. And that's it.